Hi, my name is Reagan Mccort, and today I'm going to talk to you about diamonds.
And we all lose our charms in the end. But square cut or pear shape, these rocks don't lose their shape. Diamonds are a girl's best friend.
Diamonds are far more than just gemstones. They're a metastable carbon polymorph. If you recall, a polymorph is a structural variance of an element. Later we will discuss one of the other carbon polymorphs. In the meantime, diamonds are one of the most unique members of the mineral kingdom. Yet, contrary to popular belief, diamonds are actually not that rare. The crystal is composed of over 99% carbon. The remaining percent contains trace impurities that influence their color and form. For example, diamonds can appear in yellow, blue, and other hues due to atoms like nitrogen and boron infusing the lattice. Diamonds are formed using extreme pressure and temperature. This all takes place deep under the Earth's surface. They are known for their incredible strength and iconic brilliance. Let's now dive into what makes diamonds structurally unique. At the atomic level, each carbon atom forms 4 strong covalent bonds in a tetrahedral arrangement. This creates a repeating pattern known as the diamond cubic structure, which is actually just a derivative of the face-centered cubic lattice. This crystallized structure makes them not only beautiful, but also chemically inert and resistant to corrosion. Due to these high, tightly packed, symmetrical bonds, diamonds are incredibly stiff. Additionally, their sp3 hybridization gives them even stronger bonds, which give diamonds their extreme hardness. In contrast, graphite, which is another carbon allotrope, has a layered hexagonal structure with only 3 bonds per carbon atom. The difference in this structure makes graphite both soft and electrically conductive. Now, let's break down diamonds' properties into 4 different categories. First, I would like to discuss diamonds' mechanical properties. Diamonds are actually one of the hardest known materials, ranking a total of 10 on the Mohs scale, which actually, in fun fact, uses diamonds as its scale. Additionally, Young's modulus, which if you'll recall is a measure of stiffness, scales diamonds around 1,000 to 1,200. Despite its hardness, though, diamonds actually have a low fracture toughness, meaning it can be pretty brittle under certain types of stress. Now let's take a look at diamonds' thermal properties. They have exceptionally high thermal conductivity, with around 2,000 watts, much higher than copper. This makes diamonds ideal as thermal insulators. However, it does not make them great electrical conductors, and actually, in its pure form, diamond is perfect electrical insulator. However, when it's doped with either boron or phosphorus, it can become a type of semiconductor. This has actually opened the doors for a lot of applications, such as quantum computing and even high-powered electronics. Moving on now to diamonds' optical properties. Diamonds have a refractive index of about 4.24. This gives them that typical sparkle and brilliance that we all think of when we envision diamonds. Diamonds are actually transparent to visible light, though. However, some of the trace impurities that I previously discussed can affect the appearance of the diamond. Diamonds aren't just pretty, though. They're also incredibly practical. So now I want to discuss a few different major applications of diamonds in the real world. First, I want to look at electrical and optical devices. Diamonds can be doped and act as semiconductors in high-voltage electronics. They can also be used as ultraviolet photodetectors, high-power switches, and as I previously mentioned, they have a lot of applications in quantum computing. Another area diamonds can be used is in the industrial world. Diamonds are frequently used as different cutting tools, saws, drills, and grinding wheels. This is all due to their incredibly high hardness. They also play a key role in abrasives and different polishing tools. Lastly, I want to look at the jewelry industry. This is the industry we're probably all most familiar with. Diamonds are prized as beautiful jewels. where their value is largely dependent upon 4 different categories. These categories are first cut, then clarity, color, and lastly carat. Diamonds are judged and appraised based on these 4 categories. However, more recently, there have been a rise in lab-grown diamonds. These diamonds are chemically and physically identical to natural diamonds, offering similar optical and structural properties. However, they can even be better than natural diamonds because the lab can have complete control over the different kinds of trace elements that infiltrate the crystal structure. To conclude, I find diamonds to be one of the greatest materials that we have available. From their strength, conductivity, optical clarity, and chemical stability, I find them to be useful in everything from cutting tools to quantum computers. In the future, I hope to see more research into synthetic diamond production, as there are some questions about the ethical nature of diamond mining. Additionally, I hope to see far more applications around quantum sensors and even next-generation semiconductors. So whether it's dazzling in a ring or it's silently powering your devices, diamonds are truly one of nature's most